Hello everyone, and welcome to Week 8 of Abarso's 10th grade math Google Classroom. This week we will be reviewing how to convert numbers between numeral systems. We are going to focus specifically on conversions between binary, decimal, and hexadecimal systems. Let's start with the do now. The table is showing numbers between 1 and 5 in both decimal and binary. What is the binary representation of 6? Pause the video if you need time to think about it. If you remember anything about binary, then the do now should have been very easy. The correct answer is 110. In fact, it was possible to solve it without using any formulas, just by looking at the previous numbers in the table and noticing a pattern among them. Most of the times, however, we will not be able to get the help of a table like this, and the numbers will be much greater. Therefore, in the next few minutes, we are going to review the formulas and practice with greater numbers. Before we do any calculations, let's begin with some vocabulary and theory related to numeral systems. A number is a concept or idea of a particular quantity. The same number can be expressed in many different numeral systems. For example, the number of cats visible above could be expressed as 5, written using a digit, 5 written in English, cinco in Spanish, or 101 in binary. A numeral system is a specific writing system for expressing numbers, using digits or other symbols in a consistent manner. For example, the digit 5 and Roman numeral V represent the same value, just in different numeral systems. It is very important to know in what numeral system a number is written, or otherwise we may understand its value incorrectly. A digit is a single symbol used to represent numbers according to some numeral system. You may think of digits as the building blocks of numbers in the same way as letters are the building blocks of words, at least in the English language. Another important concept is the positional notation or positional numeral system. Positional system is a numeral system in which the contribution of a digit to the value of a number is the product of the value of the digit by a factor determined by the position of the digit. For example, in decimal, which is a positional numeral system, the first digit on the right represents units, the next one tens, the next one hundreds, and so on. Therefore, even though the number 55 consists of the same two digits, 5, 5, they contribute different values to the number, 50 and 5, depending on the position. Although this may seem very natural to you, keep in mind that not all numeral systems are using positional notation. This video, however, covers only conversions between positional numeral systems. A concept related to positional systems is radix, also called base. Radix is the number of unique digits used to represent numbers. In decimal, the radix is 10, and in binary, the radix is 2. Radix is directly affecting what value a specific digit position in a number will contribute to its value. Here we can see the relation between the base and the value by which a digit at a specific position has to be multiplied by in a positional notation in order to get the value of a number. In general, the digit at the first position from the right has to be multiplied by the value of base to the power of 0. The digit at the second position from the right has to be multiplied by the value of the base to the power of 1, the next one by the value of the base to the power of 2, and so on. Specifically, in decimal numbers, the positional values of digits are, starting from the right side, units, tens, hundreds, thousands, and so on. In binary numbers, the positional values of digits are units, twos, fours, and so on. In order to get the value of a number, we multiply digits by their positional value. For example, 101 in binary has a value of 5 because 1 times 4 plus 0 times 2 plus 1 times 1 is equal to 5. Notice that the first digit from the right side will always signify units, no matter in what base is the number. This is because any base to the power of 0 is equal to 1. By convention, the base of a number is written in a subscript immediately after the number. However, for base 10, it can be omitted, as it is the most common way to express the value. You may be wondering, what is the point of learning about other numeral systems if everyone in the world is using only the decimal system in daily life? But are you actually sure that all humans are using base 10? Different cultures were evolving in different ways, and in fact, using decimal numbers is not something universal for all humans. Although other bases were more common in the past, even today there are still languages and cultures that are not using base 10. Sometimes influences from past cultures that were using different numeral systems are still shaping our present world. Have you ever wondered why an hour is divided into 60 minutes? It is because the division comes from the Babylonians, who were using a numeral system with base 60. You may think that decimal is the most logical and natural numeral system to use, because we have 10 fingers, and kids usually start learning counting by counting their fingers. However, it doesn't mean that there is no reasoning behind using numeral systems with a different base in other cultures. For example, some Native Americans were using base 8 for counting, simply because instead of counting fingers, they were counting spaces between their fingers. Counting to 12 with fingers is also not an issue if we are counting finger segments and use the thumb as a pointer. Even though other numeral systems may look strange to us at first, there is always some reason for why anyone is using it. For those who are not really interested in anthropology, there are other practical reasons for understanding numeral systems other than decimal. You may have heard that computers are using binary numbers. While it is true, this statement does not fully express the huge importance of binary numbers in today's world. Binary numbers are used by almost all electronic devices. Knowing them is essential not only for understanding computers, but also smartphones, medical equipment, communication systems, and other equipment using digital data. Right, you may never encounter numbers that are not in decimal if you are just using your computer to browse the internet. However, that may not be the case anymore if you are interested in creating and fixing things. For example, if you have ever tried to learn how to create websites, you may have noticed that colors are commonly expressed in hexadecimal numbers instead of decimal. Hopefully you have learned something new about numeral systems. While you are not required to remember what numeral systems the Babylonians were using, the more details you know, the easier it is to understand the world that surrounds you. Now it's time to do some math. Let's convert the binary number 10011 to decimal. If you remember how positional notation works, you should know that in order to find the decimal value of this number, we need to know what are the positional values of each digit. We can find them by raising the base to the power of the position of the digit, keeping in mind that the positions start from 0 and from the right side. So the first digit, from the right, has a positional value of 2 to the power of 0, which is 1. The next digit has a positional value of 2 to the power of 1, which is 2. Repeating the process, you just find that the next positional values are 4, 8, and 16. Now the only thing remaining is to multiply the digits by their positional values, which gives us the final value of 19. Let's do the opposite process. We will convert decimal number 53 to binary representation. The easiest way to do this conversion is to divide repeatedly by the base, which is 2, keeping track of the remainders. These remainders read from the bottom to the top and make up the binary number that represents 53. If you're not sure if the answer is correct, you can confirm it by converting the binary number back to decimal using the method from the previous slide. Converting between hexadecimal and decimal may appear more difficult, but in fact we are going to follow the same procedures as in the case of binary and decimal. The only difference is that we are using different bases. Hexadecimal numbers are using 16 different digits. While we would invent new digits for values between 10 and 15, the convention is to use letters. So after 9, we have a digit A, which means 10, then digit B, which means 11, and so on. Like in the example of converting binary to decimal, we should start by determining the positional values. The first digit from the right represents units. The positional value of the next digit is, as before, the base to the power of 1, which is 16 this time. The positional value of the next digit is 16 to the power of 2, which is 256. By multiplying the positional values with the digits, we get that A5 is equal to 165 and 100 is equal to 256. Notice that for the multiplication in the first example, the value of A, which is 10, was used. This is because at this point, we are dealing with decimal numbers. To convert a number from decimal to hexadecimal representation, we can divide it repeatedly by 16, keeping track of the remainders. These remainders, read from the bottom to the top, make up the hexadecimal number. If any of the remainders is greater than 9, then it should of course be replaced with the equivalent hexadecimal digit. In our example, 13 was replaced with digit D. So far, we are dealing only with conversions where at least one of the numbers was in a more familiar to us decimal notation. But what about converting numbers between two different than 10 bases? The method that always works is to convert the original number first to decimal, and then from decimal to the base we are looking for. For some pairs of numeral systems, there are, however, methods that are easier. For example, when converting hexadecimal to binary, we do not need to care about the value of the number we are converting. Instead, we can care only about the values of individual digits and convert them to binary individually, always one hexadecimal digit to exactly 4 binary digits. Converting hexadecimal F5 to binary requires us to start with replacing F with binary 1, 1, 1, 1, because F is 15 and that is 15 in binary. Then we replace 5 with 0, 1, 0, 1. Notice that we need to have the 0 at the beginning in order to have exactly 4 digits. We end up with the binary number 1, 1, 1, 1, 0, 1, 0, 1, which in fact equals to hexadecimal F5. Remember, this method of converting individual digits instead of the whole number works with hexadecimal and binary, but it may not work with other numeral systems. For example, it is not going to work when converting from decimal to binary, so do not make the mistake of doing it. The reason why it works with hexadecimal and binary is because 16 is a power of 2. In fact, this property of hexadecimals and binaries is the reason why many computer programs display binary data in hexadecimal. The conversion between these two is very easy for humans, and representing a number in hexadecimal has the advantage of being more compact and easier to read. Now it is time for you to test your skills. Complete the table by converting the numbers between binary, decimal, and hexadecimal. The answers will be displayed on the next slide, so pause the video now so that you have enough time to complete your calculations. Take the time now to check your solutions with the following answers. Thank you for watching this video. Do not hesitate to contact us either through the Google Classroom or through email if you have any questions, and remember, we're always here to help.